Okay, thank you, Bojan, for inviting TECNALIA and also the member consortium to present the project. I have split my presentations in two parts. One will be more in the TECNALIA activities, but mainly focused to CO2 capture and use. And the second part will be on the member project. So it's a few words about TECNALIA. TECNALIA is a private non-profit research organization. We are around 1,400 people. And we are the first private organization in Spain regarding project contracting and participation in the EU Horizon 2020 program. We, by the end of September this year, we were participating already in 306 projects and coordinating 63 projects. We have 6 main divisions that will be more industry and transport, where we have advanced manufacturing technologies. And you have a sustainable mobility, what is also in industry and transport. We have urban ecosystems, what is a division of sustainable buildings. We have the energy and environmental division, where we work on energy transition. And we have the health division as well, and working as well in his own, but supporting all the other division is the ICT digital, let's put in this way, division. And besides to this, we have another service on that where we provide laboratory service to companies, and we have this activity. We have R&D projects and innovation projects, and also we have a TECNALIA Ventures, a small company, a spin-off from TECNALIA to just put in the market the developments we do in the company. And regarding the CO2 capture and valorization, we work in the whole chain. The people working here is mainly people from the materials and process business area, but mainly with 3 departments. It was the membranes technology and process intensification department, where I belong. But there's also the sustainable chemistry department that is working more on CO2 use. And also we have the waste valorization department, where we have the ionic liquids expertise. So we work in membranes, absorption and absorption materials, and also with membrane reactors or microstructure reactors and fluid reactors and catalyst design and CO2 mineralization. So in one side, we work for capturing the CO2, trying to have the highest purity, and also to use the CO2 to valorize and to produce chemicals or energy vectors, such formic acid, methane, methanol, and methyl ether, and to develop high added value products. So in the field of CO2 capture, we mainly work with membranes and from our department. Also, we have people from the sustainable chemistry working in absorption and adsorption materials. And we work with several types of membranes. We have polymeric and mixed matrix inorganic membranes. Hollow fibers. You start with flat membranes, but we have spinning lines to work and develop hollow fibers, mixed matrix membranes. We also develop carbon molecular sieve membranes. We also have metallic membranes, palladium and palladium-based alloys. And also we have done some activities on metallic hollow fibers. And here are some projects. They are from biogas on grading, from that is a regional granted project. We have the M4 CO2 for CO2 capture for pre and post combustion using mixed matrix hollow fibers. That is Horizon 2020. We have the member project. I will talk later on about this. We have other projects where we develop hollow fiber membranes from bio-based copolymers for biogas upgrading or natural gas upgrading, and CO2 capture in post-combustion treatments. Or as you see, this project are mainly related to purification or biogas upgrading to inject the biogas in the natural gas grid, or CO2 capture. Also, we have some projects regarding the mineralization and capture of CO2 and develop materials that could be added later on to buildings, for instance. When we talk about the valorization, what is a chemical sustainable department, we try to valorize these chemicals, the CO2 to chemicals or niche vectors like formic acid or methane, methanol, dimethyl ether, and so on. And here you have also some project that okay, there's well, we have 3D micro reactors also for developing dimethyl ether materials for CO2 utilization from CO2, for instance, or we have biotechnological process based on microbial platforms for the conversion of CO2 from iron and steel industry, or could be the cement, or also the electric power industry. And here the people working lignocellulosic materials to obtain monomers, and from the monomers they develop, they have the building blocks for developing polymers, for instance. Also have a glycerol carbonate synthesis from CO2 and glycerol. So there's different projects we have. Is a list, and there are more projects as well. But okay, I think it's fine to show some hints of the capacity of TECNALIA. And the member project is a project that was also granted in the same call of Genesis, in the same topic. And we develop advanced membranes and membranes-assisted processes for pre- and post-combustion of CO2 capture. We'll go through fast. So the aim is to reduce the cost of the carbon dioxide capture technologies and to fight against climate change. That's the aim is to reduce the cost. It was already said before, where one speaker main issue is the cost. And we build this project based on best materials and technology from 3 previous Horizon 2020 project, or FP7 project, sorry, was M4CO2, where they were studying a large range of MOF and MOF-based mixed matrix membranes for CO2 capture, from post and pre-combustion CO2 capture. There was also a fluid cell project where we developed palladium-based membranes. This was for developing a microchips combined heat and power fuel cell system based on bioethanol with fluidized bed membrane reformer, where we have palladium membranes. And then there was the absent FP7 project that they were focused on suction enhanced reforming, and they were developing sorbents and developed this technology for hydrogen production with integrated CO2 capture. So, okay, let's move. So as I told you, the main idea was to scale up and manufacture these materials. So it's not only to go and demonstrate that the materials and the membranes or the processes performs well at TRLCs, is also in scaling up the production of the raw materials and membranes. There was it's like having a manufacturing readiness level to 6 as well. So for both CO2 capture in power plants for pre and post combustion, and also for hydrogen generation system with integrated CO2 capture. We follow, as you can guess already from my previous work, we are approaching this project with 2 different concepts. One is to use advanced mixed matrix membranes for the pre and post combustion of CO2 capture in power plants. And so and the second one was a combination of metallic hydrogen membranes, okay, this combination of metallic membranes to separate hydrogen, and sorbents to separate the CO2, and both integrated in what we call a membrane-assisted Thomson-enhanced reforming process, where we produce pure hydrogen with CO2 capture in the same process. Why mismatched hollow fibers? I think we have already seen some presentation before, because having hollow fibers, you can increase the surface against the volume to separate current streams. And then when you add them off, you try, there's a trade-off between the permeation and selectivity. What every research group is trying to do is to increase the permeation having a high selectivity. So the concept is to add the metallic organic frameworks to develop a novel pre-combustion membrane for hydrogen, for CO2 separation in pre-combustion, or for in the post-combustion, we develop membranes to separate CO2 from nitrogen. And here we start from the two best mismatched membranes that were identified in the M4CO2 project. In the other side, we have the membrane-assisted Thomson-enhanced reforming concept, that where you have the first reactor where you have the hydrogen production, where you have the membranes. This is one of the options that is, as is public, I can show the image that I can tell you about it. And you have the sorbents and the catalyst in the reactor there. You have the reforming process. You have the capture of the CO2 by the calcium oxide sorbent, and then and you have the purification of hydrogen through the membranes. The sorbent and catalyst moves to the second reactor, and where you have the regeneration of the sorbent, and then you complete the loop, moving again the sorbent and catalyst to the first reactor. And in parallel, so you can separate, when you do a regeneration of CO2, you separate the CO2, but in the first reactor, you are extracting the hydrogen from the reaction. So there will be three prototypes. One prototype is for pre-combustion capture in power plants. They will be in a biomass gasifier at CENER in Spain. So we have the bio-carbon capture sequestration demonstration there. The second prototype, we target the post-combustion CO2 capture in power plants using the combined heat and power facility of Agroguer from Galp in Portugal. And the prototype C will be to demonstrate the performances of the membrane-assisted Thomson-enhanced reforming for pure hydrogen production, and integrated CO2 capture. And the testing plan is in High Nord in Norway. So we have some targets regarding CO2 capture percentage. We are targeting more than 90%. And the capture cost is around 30 or 40, depending on the demonstrator. The consortium is formed by 17 partners from 9 countries. It's a multidisciplinary complementary team. Very industrial-oriented consortium. We have 11 small and medium enterprises and industries, and only 6 research and universities, and one of the research centers is a demo plant. So that means it's a highly oriented project. And you could see here the value chain where the partners are involved in. We have the core materials we have for the mixed matrix, MOF are developed by Johnson Matthey. I think we will have a presentation later on of the capacity of Johnson Matthey on MOF. And polymers are provided by Arkema. And the they do mainly the scale up of the raw materials there, besides developing the best MOF and size and to be implemented later on in the hollow fibers. TECNALIA is more working on the pre-combustion CO2 capture with a spinning line, and Polymen will do the work more for the mixed matrix membrane for post-combustion CO2 capture, but also they will scale up also the membranes for the pre-combustion line. That's why we have an industry. You will see that there is an industry to take over for the exploitation later on. So in doing this, we have to when we do when you scale up on materials or components, you have to control the process, and so you look for the reproducibility, homogeneity, and to keep the properties in different batches. And also when you might be, instead of having a small amounts in each batch, you do a big batch, and you have to also demonstrate the reproducibility and of the materials you do, polymers, MOF, or membranes, and then all the people working on this are involved. And then we have the activities related to developing the modules and also the CO2 capture systems. For the modules here, for the demonstrators are developed by Polymem, and High Gear, also with the support of TUDEL, they are developing the two, let's say, separation system for the post-combustion and the pre-combustion. And in this case, we already have the process book and the engineering book developed, and we are buying and the components. We're doing all the procurement and buying and building the prototype. In the case of the biogas plant at Sener, we are also, but not by High Gear, it's mainly by KT and Eindhoven University. They are developing the syngas cleaning system as well. And then they will go, the prototypes by the end of the next year, they will go to the demo sites. We also have electrical analysis that is carried out by Quantis. And then we have the master concept, where we develop sorbents, catalysts, and palladium membranes. When we say we develop, we are scaling up to 200 kilograms of sorbent, for instance, a large scale production of membranes, and also catalysts. We are increasing the manufacturing readiness level. It's the same approach as before. We have to control the quality and the reproducibility of properties and of the materials we develop. And also we are talking about recyclability of, in this case was palladium membranes, and also on the recyclability of the membranes itself in both cases, also in the mixed matrix membranes and the palladium membranes. We have KT and Eindhoven University developing the reactor, and this will be integrated in IFE facilities for the demo site, and because it's with the there will be a reactor. I show you there was the master concept. There was two parts. There was the reactor zone and the regeneration zone. So we will use the regeneration zone that is already available, and we will change the reactor. Okay, and there will be other balance of plant adaptation as well. And then also, and in this case, we also have the engineering book finalized, and they are doing the building of the reactor prototype that will be by the end of the next year put in the demo site for the testing. The main expected results will be the first one, that's the prototypes, let's do, for the 3 lines. But we also have mixed matrix membranes for combustion, for pre and post combustion, that could be applied in other processes. And also we will have sorbents and catalysts that could be also used in other, because we are scaling up the sorbents and the catalysts, and the membranes and also a new design of the social hash reforming. And this demo site will be compared to 3 reference systems with and without capture. Like you have here the 3. We have the integrated. I think this is the integrated gas combustion. I think plan. I think is the name of the. Yeah, okay. Integrated gasification combined cycle, and then you have the coal power plants with amine absorption MIA or MDA with the steam reforming process absorption for CO2 capture. So this will be the references we will compare our process, and that is all. That's